Hey guys, my name is Ashton Roharia and I'm a grad student at Georgia Tech studying computer science, and I'll be giving a presentation on the paper Reverse Engineering IoT Devices, Effective Techniques and Methods. This paper can be used to better understand how to build secure IoT devices by showing security flaws in existing IoT devices exposed by reverse engineering. First, I want to give credit where credit is due. This paper was written by Omer, Yael, Michelle, Yuval, and Yossi, and they're all from an Israeli university. This paper was published in 2018, so the research presented is still relevant today. I've also provided the link to the paper in case anyone finds this interesting and wants to read further. So let me begin with the topics I plan to cover. First, I'll go through an overview just talking about IoT in general and what constitutes an IoT device. Next, I'll go through the reverse engineering methodology that the paper offers. It's a generic methodology that can work for pretty much any IoT device. After that, I'll go over the results of the information that was revealed through using the reverse engineering methodology on a list of IoT devices. And finally, I'll talk about the key takeaways, such as security recommendations for designing an IoT product. So first of all, overview. The Internet of Things, or IoT, is a network of smart electronic devices with internet connectivity. Objects that existed decades ago, such as TVs, speakers, toys, and appliances, are all slowly progressing into IoT devices as they get enabled with wireless connectivity. For example, now you can easily find a smart door lock that allows you to access a traditional door lock, but with your mobile device. And other examples can just be seen in the background of the slide. The block diagram on the right shows what a typical IoT device is composed of. Essentially, it's a processor with inputs and outputs and wireless connectivity. So even though IoT devices have been around for years, we're still finding ways to make them smaller, cheaper, more efficient, and more secure, and the latter being what this paper focuses on. So to make IoT more secure, we first need to understand its security flaws. All of the aspects of the device, including the hardware, software, and connectivity, need to be secure for the system to be secure overall. Without security, any connected object, from smart refrigerators to manufacturing bots, can be hacked. Once hackers gain control, they can take over the object's functionality and also steal the user's data. Another dangerous aspect is that you don't want the IoT device to be the weakest link in terms of security. It doesn't matter how secure the rest of the system is, because if they're able to hack into the small and cheap embedded microcontroller, they could now bypass a more expensive and robust security system that the original embedded system is connected to. Because they're made to be cheap and resourceful, they're becoming an increasingly attractive target for cyber criminals. Also, since IoT devices are growing at a dangerously fast pace, more connected devices mean more attack vectors and more possibilities for hackers to target us. One alarming example of hackers exposing security flaws were in the Chrysler vehicles back in 2015. Cars are essentially large IoT devices because they contain a microprocessor with inputs and outputs, as well as having wireless connectivity, which checks out with the block diagram and the previous slide. What happened here was that Chrysler included a Uconnect system in their car, and this was able to be hacked by hackers. Uconnect was a system that controlled the car's infotainment system, maps, Wi-Fi, and other essential parts of the code. It was there to make it easier for the driver to access all of this information, but due to its security flaws, it was able to be easily hacked. Hackers were able to run their own code on this Uconnect system, and what they were able to accomplish was pretty frightening, to say the least. They were able to control the high beams of the car, steering, braking, locking and unlocking doors. Essentially, the hackers could accomplish anything the driver could do using the Uconnect system. This was able to be fixed, but it required updating the firmware of the car. Firmware has traditionally been tricky to update, but slowly over-the-air wireless firmware updates are becoming more popular and accessible. In 2015, the Chrysler cars weren't capable of the over-the-air updates, so they had to recall millions of cars just to update their firmware manually. And once they were recalled, they would have to be worked on for quite a while. So this was inconvenient for both the company and drivers of the car. Another example of security flaws in IoT systems happened in something as simple as a smart coffee machine. Coffee machines are generally not designed for security, and neither are other small and cheap IoT devices. And if they're not secure, all they are essentially additional vectors to get into the networks. And we can do that by using the reverse engineering methodology. This methodology contains 3 steps: inspecting the device, extracting sensitive data such as firmware, and then finally analyzing that firmware to reveal sensitive information. I'll go into each of these steps in the following slides. So first we've got inspecting the device. This is essentially taking it apart and looking at what you've got to work with. Taking apart existing IoT devices is possible in most cases since they're just encompassed in metal or plastic and they're just held together by screws and glue. So once you've opened up the device, the first step is to locate and identify the memory components. A number of IoT devices contain memory components outside the microcontroller since they need extra memory. These components are where you can find sensitive data such as the user application, boot code, bootloader, a wireless stack, or any other essential components of the system. So after you've located any memory components that may exist, you want to try to locate the UART terminals. UART is a very standard and simple communication protocol, and it's used in a lot of embedded devices. The reason we're interested in this is because connecting to a UART port would allow us easy access to communicate with the microcontroller or OS of the IoT device. Finding the UART terminals would require you to find the 3 electrical lines needed for UART, and that includes the transmit, receive, and ground pin. The 3 images at the bottom show you how they could appear on some example boards. The paper also describes a really cool tool that's publicly available on GitHub, and it essentially lets out an audible beep whenever it touches a UART transmit line, and that's because it's detecting a few ASCII characters. So once you've found any UART terminals that may exist in the IoT device, you can move on to the next step, which is extracting the data, which in our case is extracting the firmware. This paper explains how you can extract firmware using these 3 steps. The first step is to access the bootloader when the boot process begins. Since the bootloader has a pretty small memory footprint, it usually doesn't contain complicated code such as password checking logic. Instead, it may only perform a single string comparison against a hard-coded password, and this hard-coded password could be recovered from the memory. Next, you could use physical attacks to bypass passwords. A fault injection could be used to generate a hardware fault, and that could manipulate the underlying software. This paper describes an example of a fault injection, and it's done through shorting a SPI flash pin with the ground. This caused the system to fall back into a process with elevated privileges, and this could be pretty dangerous in the hands of a hacker. Finally, you want to extract the firmware and obtain it. Getting your hands on the firmware can expose major secrets and vulnerabilities of the device. One way you can do this is by reading over UART from a bootloader. The bootloader often contains memory read and write functionality, and that can be used to slowly dump an image of memory into a UART console. If the bootloader is inaccessible, flash memory can also be extracted through minimally intrusive ways, such as connecting a logic analyzer to the pin of the memory module and recording the signals during boot up. Another interesting way is to simply desolder the memory chip and connect it to an off-the-shelf memory reader, but desoldering could be pretty tricky and result in destroying the chip as well. So once you've got a hold of the firmware image, the next step in reverse engineering the IoT device is through analyzing the firmware. This paper doesn't go into too much details over analyzing the firmware, but it still does list these 3 steps. First, you want to unpack the memory image obtained in the last slide, and this can be done through some pretty easily accessible, publicly available tools. Next, you can bypass passwords you encounter in the code using brute force methods. This can also be found and done through publicly available tools. And finally, it's up to the hacker to detect vulnerabilities within the firmware. The firmware images contain the OS and code controlling the hardware behavior, so taking some time to understand it may expose some vulnerabilities. So now that we've gone through the methodology for reverse engineering IoT devices, let's take a look at some of the results of what reverse engineering can expose. So here we've got a list of the IoT devices that the paper tested its reverse engineering methodology on. Some of the devices include IP cameras, and IP cameras are just a type of digital video camera that receives control data and sends image and video data via an IP network. We've also got baby monitors that are similar to this. They both record video. And then we've also got doorbells, smart doorbells to be specific, and they allow the control of opening and unlocking doors and gates. And then finally, we've got smart thermostats. All of the devices in the last table weren't able to be reverse engineered into, which is a good sign. That means hackers weren't able to pick up any IoT device and access sensitive data just through a few steps. The ones shown in this table did show some signs of faulty security. For example, in the first device, the researchers were able to bypass a terminal password just by shorting the memory. Another example is that the second device, the onboard flash could be physically read using reverse engineering. Both of these devices are smart camera, so it's a bit alarming that these off-the-shelf smart cameras have these security flaws. Here were some of the discoveries that were made during the evaluation. So first we've got login credentials. These are credentials of the user accounts on the device. Next we have Wi-Fi credentials. This is the network's password, which if you think about it, has to be stored somewhere in the embedded device if it's connected to the internet. Next one is remote access, which is more of a feature than it is data that is exposed. This means users can log into the IoT device without being in proximity to it, which is pretty dangerous for devices like cameras. Private keys were also compromised, which allows encrypted data to be decrypted by the hacker. And finally, device rebranding was also detected. This shows where the part originally came from. Rebranding is pretty common for IoT devices. Generally, IoT device providers get their silicon from well-established semiconductor companies, so this discovery would show which companies they originally got their silicon from. Finally, we can talk about the key takeaways of this paper, which happens to be how to avoid someone easily reverse engineering your IoT product. So we've got a list of security recommendations, which shouldn't be a surprise at this point, since all of these were used in the reverse engineering methodology. First, we should remove any unnecessary UART ports whenever possible. If they are necessary, then you can restrict access to them by making them read-only. And then finally, if they need to be write-enabled, we can still protect the UART ports in a similar fashion to JTAG protection. Number 4 is that we can harden bootloader security using passwords or only allowing debug mode when a specific electrical criteria is met. And then we've also got to make sure that unique passwords are used per devices and not just one password across the entire manufacturer. And then we've also got that password replacement should be possible by the user so that it's not just hard-coded into the device. We also want to be able to encrypt device memory and sensitive data whenever possible. And finally, pen testing products should be done before they are launched to prevent people like you and me from hacking and exposing security flaws just by following a few simple steps. I hope this presentation taught everyone about the significance of IoT device security and how reverse engineering IoT devices can not only expose us to security flaws, but also teach us better and more secure development techniques going forward. Thanks everyone, and have a great day.